So we're going to start a new topic today, which is streaming with Kafka. So previously in the course, we have seen distributed static data processing with Hadoop, Pig, and Spark. So now we're going to move on to distributed processing of highly dynamic data, in this case, streams. So we're going to have one class on this, which we're going to introduce Kafka. So thus far, we've looked at files that have been static, basically what are sometimes called data lakes, where we have basically a bunch of data residing in HDFS or in Spark that we'd like to process. So the key things here are that we have some batch processing, and we want to run some queries over these data. When we talk about streams, we talk about dynamic data that are constantly flowing into the application, and we want to be able to analyze them and to extract some value from them. Yeah. So in this case, we talk about event processing, continuous querying, and real-time response. So event processing would be to try to detect potentially complex events that are happening. Some continuous querying means that we register a query and we want to receive a stream of results for that query rather than running a query once off. And real-time response, often in these scenarios, we want to take action in real time based on, for example, the events that we analyze. So to take some examples of applications where we might have some streaming involved, here we have social media analytics. So an event would be that maybe a video goes viral, or we get a burst of tweets about earthquakes. Spoiler for the lab that we'll see on Wednesday. Okay, we'll be looking at tweets about earthquakes. Continuous querying. So an example would be to track sentiment for a company's product. So if we see that there's a major backlash against a certain product of our company, that could be considered a query that we could register. And to monitor popular users tweeting about me. So I can maybe launch a query and say, tell me when somebody with more than 100,000 followers mentions me, or whatever it might be. Real-time response might be in the earthquake scenario, for example, to let the emergency services know that lots of people are tweeting about the earthquakes. We might want to schedule a quality control review if our product is getting very negative messages on Twitter and so forth. A very common application that we will see more in the computer science area is log monitoring. So if you have some very complex web application that's being used by thousands and thousands of users, you might have these logs that are being produced, where we might have some typical debug or info messages that makes it seem like everything's okay, but we want to detect errors to see if there are common types of errors. So event processing would be, for example, a burst of log messages. Maybe a service has failed and is creating a burst of errors. Some critical error message that indicates, for example, that in a bank, some integrity constraint in the database is being violated, or whatever it might be. Continuous querying would be to track the most critical fixes today. So to collect somehow what are the trending critical fixes or error messages that need to be fixed. Monitor memory leaks in the new release, whatever it might be. Real-time response would be to disable unsafe features in a website, maybe provide some messages for users. Maybe automatically fire the new developer who we think might be responsible for all these errors. I'm not recommending that, but okay. Another application, finance. So an event could be that a company goes public, a stock drops sharply. Continuous querying, where we want to track maybe stocks with gains of 10% in a single day. Create alerts for major buy-sell transactions. Real-time responses typically would be to buy stocks, to sell stocks, whatever it might be. Astronomy is a key application in this university, and the astronomy people from the faculty are using Kafka for processing astronomic data. What kinds of events could we consider? Maybe a telescope moves and we're suddenly looking at some new region of the sky. Maybe a light source flashes and we think it's an astronomic body. That could be maybe a transient body. Yeah. Some continuous querying examples: find possible supernovae. So these are bright objects that did not appear before and have certain characteristics. Maybe to track an object across the sky to understand when its position moves. Real-time response might be to refocus another telescope on an object that we feel is important, for example, to capture a transient supernova while it's still around, maybe to lower data filter thresholds to allow more light into our sensors. Yeah. Or to capture more data, not to filter data that we would typically consider to be uninteresting, but now might be interesting because of an event. So these are some also streams. So if we talk about streams, we have Internet of Things. Has anyone taken a course on Internet of Things? I think there's a new course on this. So the idea is basically that we have all these sensors and devices that are connected to the internet and can communicate for smart applications. So event processing, a light turns on or starts to rain, continuous querying, tell me when the temperature reaches a certain point or in what rooms it reaches a certain point, update the position of a vehicle in real time. And then responses could be to turn off air conditioning, turn on air conditioning, change the lighting, take another route, whatever it might be. Yeah. So this is to give a flavor of some of the scenarios where we could be talking about streams and looking at different ways of processing streams. So if we have a massive stream, what we would like to have is a distributed streaming platform that can handle a very fast, large current of messages, yeah, of data coming in. There is quite a number of available platforms for processing streams in a distributed setting. So we have Flink, Apex, Storm, Apache Spark has streaming services, and this one is Kafka, as you can see from the K, right? So essentially, we're going to be focusing on Kafka in this class, and we're going to be looking at since we're in Chile, the home of natural disasters, we'll be looking at an application based on emergency responses. Yeah. So it's a little bit strange being from Ireland that there can be earthquakes and volcanoes and forest fires and not much happens. But if it rains for more than 2 hours, that seems to be the most serious problem that happens in Chile. So, okay, what happens in this scenario? We're going to assume that we have a fire department, we have a health department, and we have a police department. And we have some streams of data that these departments would like to keep up on track of. Seismology data, weather reports, hotline for emergency calls, Twitter or social media, where we might be getting reports related to the emergency, news outlets, and traffic reports, right? So all of these sources could somehow be relevant for dealing with or understanding an emergency. Yeah. So we assume as well that we have some static data, maybe in databases, for example, a database of places, of geographic locations in Chile, and also maybe a database of events, of somewhere where we're storing the key events during the emergency. So in general, if we look at this system and we look at how data are being processed, these streams of data that are coming in, we could say that all 6 of these are relevant for the fire department, right? They need traffic reports because they need to understand how to get to somewhere quickly. They don't want to be stuck in traffic. They need access to who's reporting what fires. They need access to all this information. You know, maybe for health, they're more interested in the hotline, like where the health emergency is being reported, and also the traffic to make sure that they can get there quickly, right? And maybe we'll say that the last 4 are relevant for the police department. They don't really care so much about seismology or the weather, but they care about the emergency hotline, about Twitter for crime reports, news, and traffic information. Yeah. Aside from this, we can assume that the departments also consume static data from different databases, for example, from maps and different geographic situations. So if we connect all of the data that all of these different departments need and all the streams of information they could be interested in and so forth, and also consider that they might also be sharing information amongst each other. For example, the fire department might be sharing information with the police and the health people, and the police might also be informing the health services and so forth. What we see is that we get a mess. Yeah, we have all this sort of mix of information flowing all over the place. And we have all these connections, and really it's just kind of very difficult to know what's going on. Yep. So in this sort of scenario, the idea is that we're going to put something in the middle here. We're going to put something in the middle that will help to coordinate the messages, the production of messages and the consumption of messages. When I say a message can be a seismology reading, it can be a tweet, it can be a news headline, whatever it might be. Yeah. So we're going to put this thing in the middle, and then we're going to somehow coordinate the flow of information or messages through these different entities using the central, we could call it a broker. Yeah. So essentially, this way we don't have this sort of n squared problem of connecting everything to connecting. We connect everything into one central coordination point, and that's Kafka. Yeah. Okay, so this is Apache Kafka. Why is it called Kafka? Well, you might have heard of Franz Kafka. We can do our usual trends analysis to see which is more popular. And we see that Apache Kafka is now bigger than Franz Kafka. Franz Kafka being the novelist. Yeah. Why is it called Franz Kafka? Someone who wrote Apache Kafka, who would have been in LinkedIn, was a fan of Kafka. So there we go. So Apache Kafka is open source. Like many tools in this area, it's written in Scala or Java. So in big data, the JVM is seen as quite convenient. It allows for interoperability across different machines and so forth, but also offering pretty good performance. Maybe not as good as C or C++, but can be competitive with just-in-time compiling and so forth. And it originated in LinkedIn. Yeah, so in LinkedIn, they had a need. They had this sort of problem that we saw, that there was all these messages and notifications and errors and logs and so forth. And they wanted to begin to organize this in some way. Yep. So any questions or doubts so far? Okay, so in terms of the overview of Kafka, we're going to look at different features of Kafka, but the first thing we're going to look at are the two main concepts of producers and consumers. And this Kafka allows us essentially to have two things that we usually don't have at the same time. We can have push and pull at the same time. Yeah, so usually something is push. So let's say you receive some content, it's pushed to you. Or it's pull. You send a request and you receive that information. Here, producers push, they push the information, and the consumers pull the information, they request the information. Why is it a problem to have both of these things at the same time? Because how do you coordinate, right? If the producers push and the consumers don't pull at the same time, then you have this thing that's just sitting there, right? So this is what Kafka allows you to do. So producers can push to Kafka. Kafka implements what we could see as a buffer of messages, and then the consumers can pull when they need to read those messages, right? So we can see Kafka as a sort of a distributed buffer of messages. So a message comes from the producers, and then it gets sent to one or more consumers. Sorry, so we can have multiple consumers reading the messages pushed by the producers. So the main data model used by Kafka is the notion of a record. Yeah. So the record is what forms this buffer of messages, what we'll call the ledger. Yeah. So we have a record which is composed of an offset, a timestamp, and a key value pair. Yeah. So records represent events, essentially, or messages. Yeah. Records are immutable. So once they're written, we're not going to change them ever. Yeah. They contain an ID or an offset, okay, a timestamp, a key, and a value. So the timestamp can be assigned by the application or left to Kafka, which will associate a system time with the messages. Okay. So in terms of the ledger, the producers can essentially push messages which will be appended to the ledger. And we keep a strict offset, right? So essentially we have some increasing ID for each of the messages. Yeah. So we keep all of the messages in the order of this offset. Okay. And so on. So the producers always append to a ledger when they push a message. So producers may only append to the ledger. The messages are immutable, which means that they can never be changed. So producers are always adding to the end of the ledger, and they can't change something that's already been pushed. The consumers can then essentially read from anywhere they like. Yeah, so they don't have to read from the end necessarily, although in most cases that's what we're going to do. But consumers, in theory, depending on the configuration of the ledger, can read from anywhere in that ledger. Yeah. So while producers may only append to the ledger, the consumers can read from anywhere in the ledger, kind of. Yeah. So it depends on how we've configured the ledger, and it will have a cost associated if we permit this. So what this means is that consumers can also replay messages. They can go back to a certain point, replay some messages that they wanted to see again, whatever it might be. Questions or thoughts? We good? Okay, so we have ledgers, and the next important concept for Kafka is the notion of topics. So essentially, topics allow us to define somehow some high-level categories of different ledgers. So we might have one topic in this emergency scenario relating to disasters, to earthquakes, volcanoes, forest fires, whatever it might be. Another topic related to news. So we want to see what the news outlets are reporting. And a third topic related to traffic. So then we can connect the different streams and produce messages within a given topic. Yeah. So we have these different topics. So for example, let's say Twitter is relevant for traffic, and also obviously traffic reports are related for traffic. And then the consumers can subscribe to a topic to say, hey, I want to receive the messages related to this topic. Yeah. So in this case, we have some subscriptions where the consumers are subscribed to topics and will receive the messages relating to those topics. So producers publish to topics and consumers subscribe to topics. Yeah, they can pull messages from the topics they're subscribed to. Topics are persistent, so they are on disk. Yeah. We can configure a different retention policy, what is retained or kept, depending on the space, the amount of messages we're receiving, how much cost we want to associate, and what we need for the application. So the first policy is to keep everything. Yeah, we keep all the messages, all the history of messages in that topic. If we're receiving a massive stream of data, this might not be the wisest choice, right? Especially if we don't need the historic information. Another retention policy is to delete once consumed. So if we know that there's only one consumer, then we can maybe opt for this. So once it's been consumed by a consumer, delete the message, which obviously will not allow any replay afterwards. We can keep for a period of time. So we can say, okay, let's keep all of the messages for the past 24 hours. And when we get, as we receive new messages, we receive the messages older than 24 hours automatically. Yeah. So this is a sort of a window-based operator. Yeah. Or we can use a fixed amount of time, a fixed amount of space. So we can say, okay, I'm going to keep 1 gigabyte for this topic. If it goes beyond 1 gigabyte, start deleting the older messages as we proceed. Yeah. So I spoke about how the topics, the ledgers are distributed. Yeah. At the start. So how is the distribution done? So we use this key for partitioning. Yeah. So we assume that somehow all of these messages, the keys in these messages, are all assigned to this partition 1. All these keys here, we assume that they will be assigned to partition 2, and all of them, these keys here are assigned to partition 3. So we use these K values here. We can do a hash modulo to assign a partition, much like in MapReduce and in other scenarios that we've seen. So the partitions may or may not be on different machines. Yeah, so we can maybe have multiple partitions on a machine, but the most typical scenario would be to have different machines on which we have partitions, the distributed setting. So once we distribute this whole thing, once we set multiple machines working on managing different topics, things get a little bit more complex. Yeah. So there are certain guarantees that are quite feasible locally, but become a lot more difficult for partitions. So one thing that is kind of tricky when we look at partitioning is the notion of offset or ordering. So I said that Kafka will always guarantee you to have the data in order of their offset, right? This is only guaranteed per partition. So if we have a topic that's split over multiple machines, on each machine, everything will be ordered, but we may lose the global order. Yeah, there may not be any more a way to replay the messages in the same order they were received. Yeah, because we can't compare the order across the different partitions. So for ordering across partitions, we'll often need to use an application level timestamp. Yeah, so for example, if we were working with Twitter, we would need to take the timestamp from Twitter of when the message was received and try to use that to impose an order across partitions. Yeah, or some sort of time based on when a sensor registered some value or whatever it might be. Questions or doubts? Nope. Okay. So when we talk about distributed systems, again, we have to be careful about fault tolerance and so forth. So for this reason, topics can be replicated as well, not just partitioned, but also copied to different machines. So we can choose a factor per topic. So maybe, if there's a topic that's not essential, maybe for the emergency services, it's kind of interesting to see Twitter, but if it fails, not a big deal. Maybe we can define a replication factor of 1 in that sort of scenario. Yeah. If there's a more important aspect, like for example, maybe the emergency services calls to the emergency number, we might want to assign it a replication of 3 or 5, depending on how large it is and how critical it is to the services. So then Kafka, like in all these distributed systems we've seen, will take care of the exact location of the data, the load balancing and all of this. Yeah. So replication is wonderful, but we have to be a little bit careful here. So can anyone see a potential issue if we start copying things? We start replicating topics. So memory for sure. Yeah, we'll be using 3 times or 5 times or n times the space. Yeah. So here it's a different issue that we have to be wary of. And it relates, there's maybe more than one problem here, but it relates to the guarantee of order. Yeah. So if we have an partition copied on multiple machines and we guarantee order per partition, the question is, how are we going to guarantee the same order happens in the same that we have the same order in all of the copies of the partition? Yeah. So the classic problem of maintaining consistent replicas, yeah, so that they actually say the same thing. So we'll have the problem of order. Yeah. So how do we solve this? We have to make sure that within the partitions that we have the same order of messages. So how this is done is, as we've seen before in many of the different distributed systems we've seen, the standard solution to this problem is to appoint one of the copies as the leader. Yeah. So there is one partition which is known to be the leader. Yeah. The other copies are known as followers. So the leaders can be elected or chosen between themselves. Yeah. So we don't have some master to say this is the leader, but they can be chosen. So the leader then allows us to essentially ensure that we have a consistent view of each partition across the different machines. Basically, it allows us to ensure that there's, in this case, for example, order per partition. So all the reads and all the writes go to the leader. So the reads, it's a little bit weird why we care about the reads, but the writes, it's kind of clear, because if we have multiple producers writing messages to a topic, we want them to go through the leader so that we don't end up with different producers writing different things in different machines to the same partition, which would make it very difficult to maintain order. So we'll come back to that issue a little bit later as to why the reads are important. There's a couple of other concepts I have to explain first. Any questions or doubts so far? Cool. Okay. So let's first of all, let's have a look at the write guarantees. What are the guarantees for writing and how it works with this leader and the partitions and so forth? So a producer writes a message, and let's say the producer is writing a message to partition 1, for example, of a topic. So the producer will write the message to the leader, and the leader will forward that message to the followers. Yeah, this is called asynchronous writes, which means that there's no guarantee. Basically, the producer just assumes that everything went okay. There's no follow-up, no check to make sure that actually the thing was written or received by Kafka and added to the partition. So another level of guarantee is the leader commit guarantee, which essentially at least tells us that the leader got the message. We don't know if the leader actually successfully wrote to the followers or not. So this is a little bit better than no guarantee or asynchronous writes. At least we know that the leader has acknowledged that everything went okay. But we don't know if the followers picked up the message or not. The last option is a quorum. So if we really want to make sure that a message was received in Kafka, we can do a leader commit and then define a quorum that we have to receive also an acknowledgement from a certain number of followers. Yeah. So in this case, the partition sends the data. So the producer sends the message to the leader sends it to the followers. The leader waits for the acknowledgement from at least n followers. And then when it receives that, it sends the message, the acknowledgement back to the producer that, yeah, okay, the write has been successful. So in terms of write guarantees, we have asynchronous, which is basically no guarantee at all. We hope the thing is written. However, the benefit of that is it's very low latency. So we can do writes very efficiently. We're not waiting for some acknowledgement. We just send messages and hope for the best. Yeah. So leader commit, we know that at least the message was registered on the leader, and we have somehow medium latency. So we still have to wait for the leader to come back and acknowledge before finishing the write. But it's not too much, right? It's somehow an intermediate option. A stronger option in terms of consistency is the leader commit with a quorum of n. So this means that we know that the message will have been received and processed on the leader and on n follower machines for that partition. However, this has a cost. It's higher latency. It will take longer to do writes. And we have to factor in as well the network traffic, where we have additional network acknowledgements and so forth. So we see here that we have certain trade-offs between efficiency. That would be the most efficient being asynchronous, the least efficient being leader commit and quorum n. And we have a trade-off with guarantees or consistency. Yeah. The weakest consistency here is asynchronous. We actually don't even know if the thing was recorded or not. While the strongest would be amongst these options, the leader commit and quorum n. Okay. Any questions or doubts on that? No? Okay, so these are the write guarantees. And this sort of trade-off is super common in distributed systems, where we can, at a higher cost, have higher guarantees or better guarantees or higher levels of consistency. At lower costs, we can somehow hope for the best. And if something fails, maybe it's not so critical. And we that way save a lot of network, disk usage, whatever it might be. So we have these sorts of trade-offs all the time. So they're the writes. So what about the reads? So in terms of reads, the key point here is that Kafka tracks the consumer offset. Yeah. So we have to register consumers with Kafka. And as we read from that consumer, which will have an ID associated, Kafka will maintain information about where that consumer is in the current topic, yeah, where they're reading from. So here, for example, we have the consumer. Consumer here is C1, identifies itself as C1 to Kafka. It's registered with Kafka. So we know that this consumer is receiving now message with offset 1 and message with offset 2, and it processes here somehow internally those messages. So here I'm just going to keep track of what offsets have been read, but obviously the consumer could take the keys, the values, the times, whatever, do some processing and do something interesting with that. Yeah. So so Kafka keeps track of where the consumer is in this. So when the consumer says, I want to read more, yeah. So then Kafka will send some messages to the consumer, let's say offset 3 and 4. And we see that it's updated here, 5, 6, and so forth, and 7, 8, and yeah. So all this works wonderfully. The question is, what happens when it doesn't work wonderfully? Yeah, what happens when there are failures? Yeah, so there's maybe a network problem, or some messages fail to read for whatever reason. So in distributed systems, we have to assume that sometimes messages will fail. Yeah? So in this case, we assume we've read message 5, but for whatever reason, reading message 6 has failed in this case. So what can we do? So what should we do in the case of a read failure? So there are various responses to this, and it probably depends on the application. Yeah. So one option. Well, okay, so we have different read guarantees, so we can choose from different options for what guarantees we have when we read. So there are various options. The first option is called at least once. Yeah. So what does this guarantee tell you? It tells you that each value is processed at least once. Yeah. Not exactly once, at least once. So essentially the idea is that we're going to update the consumer offset only when the consumer acknowledges that it has read the data that we have. Yeah. So let's say we're reading through our data again. This consumer is very interested in this partition, reads a couple of messages, okay? Then the consumer must send back an acknowledgement to Kafka to say, I've read these messages, please change my offset, move my offset forward. So then Kafka says, okay, we know you've read those 2 messages. So here comes another 2 messages. And Kafka is waiting for the response or the acknowledgement from the consumer. But there's a failure somehow in reading these 2 messages. Yeah. So maybe only some of the messages are received. Here we see it's read 3, but we've not read 4 yet. So in this case, the consumer essentially calls again Kafka and says, hey, can you read these messages again? And the messages are sent. Okay. And then the consumer acknowledges, and then Kafka will update the offset. Yeah. So the offset is always updated upon receiving a confirmation that the messages have been read. If we see here, however, when the first time when 4 failed, we had already read 3. And then when we call Kafka again, we're going to receive 3 and 4 again. Yeah. So this is why it's called at least once, because some of the messages we could potentially read more than one time. But because we wait on the acknowledgement of the consumer to update the offset in Kafka, it means that we know that we're going to read each message at least once. Yeah. So this is the default behavior of Kafka. And this is, if you don't set any particular parameters, you can assume the at least once behavior. Another type of read guarantee is the at most once guarantee. Yeah. So at least once would be good. For example, let's say if it was the emergency hotline where you wanted to be sure that you didn't miss any message, you didn't miss any call. Yeah. It's not so terrible if maybe you process the same call twice, but you want to be sure that you definitely process each call at least once. Yeah. So we have a different read guarantee then, which is at most once, where each value is processed at most once, and the consumer offset is updated immediately. Yeah. So what does it mean? It means that once a consumer has read, we don't wait for the acknowledgement, we just move the offset forward. Yeah. In fact, we don't even care for a consumer acknowledgement because we're just going to move the offset forward, and the next time the consumer pulls some messages, we assume that the last read went okay, and we just continue forward. Yeah. So what happened in this case? Let me go back here. We see that we read message 3 okay, but somehow message 4 failed. Yeah. So what does it mean? It means that it doesn't matter. Kafka is going to continue and update the offset of the consumer, and 4 will never be read. Yeah. So this would not be a good idea for example, for an emergency hotline. We don't want to miss a call. But let's say we're processing tweets and we're looking for trends in tweets. If we miss some tweets, not the end of the world. Yeah. Especially if we have to process maybe a lot of information. It's not going to overly affect the results. It's not going to overly affect anything in the real world to maybe miss some reads. Yeah. So maybe in some scenarios, this might be a good option. What is the main benefit of this versus at least once? We have no acknowledgements. We have less communication. It should be a little bit more efficient. Yeah. So if we don't really mind too much if some messages are skipped, if we don't see that as an issue, we can apply at most once. The third type of guarantee is called effectively once. So the idea is, you may have thought of this as well when you saw at least once. It's essentially at least once in terms of the Kafka framework, but we assume that the consumers will notice the duplicate and get rid of it. Yeah. So essentially the consumer takes the responsibility of detecting duplicates and avoiding processing them more than once. Yeah. So we have our consumer in the effectively once. The consumer has to send the acknowledgement as is part of the at least once protocol. So then the consumer reads these messages here. Message 4 has failed. However, we're going to use the offset of the message to make sure that we process each message more than once. So when we receive message 3 again, we can detect that there was a duplicate somehow and remove it from consideration. Yeah. So we can use the offsets because the messages are immutable. We can use the offsets to see if we've already processed something on the client side. So the client is basically keeping track of what offsets it has already read. Yeah. And we continue in this way. We receive the acknowledgement, we update the offset, and we make sure that these messages are new, that we've not seen them before. So this is the effectively once scheme. The exactly once scheme was added to kind of later versions of Kafka, but the idea of exactly once is that Kafka allows you to gives you the guarantee that each message will be read once and only once by the consumers. So essentially the idea is that the data and offset are updated as a single transaction. So not to get into too much detail, but essentially what we're saying here is that there is now a transaction ID associated with these operations. And we can cancel transactions or we can undo transactions based on the transaction ID that we have. So this would be transaction 1, which would be this idea of the read and the update of the offset being in one transaction with these 2 operations. Yeah, so the read itself and the acknowledgement. And if something fails in the middle of a transaction, essentially like as in transactions in databases, we can undo the entire transaction. Yeah, so we can somehow capture this and undo it. So this is the idea of the transactions, transactional reads in Kafka, which are exactly once. Yeah. So with this, we have the guarantee, assuming that the system is working quite okay. The network is working okay and so forth. We can guarantee this exactly once read behavior. Of course, sorry, what's not so good about this option is the cost. We have a lot of coordination necessary in order to make sure that this is working. So we have the at least once coordination of the commits from the or the acknowledgements from the consumer, as well as the transactional support. So we have these transaction IDs and we need to manage these transactions. So this is the most costly option. So when we talk about read guarantees, how are these implemented? We have these leaders, and we have to be slightly careful that even though it would be ideal to allow the followers, to enable the followers to serve reads, we can't, or it would be complicated. Yeah. So we have 3 copies here. We probably understand why we need to write to the leader. This is to make sure we have a consistent order in the different copies, in the different replicas for the partition. Okay. What is kind of weird is that we can't read from anything here because we know that these are exact copies of the partitions, right? We know that they're consistent. So why can't we read from the followers, from the other copies? It's because we know that the Kafka is maintaining the offset for the consumers. So if Kafka is maintaining the offset for the consumers, that also needs to be consistent. So it's somehow like Kafka is writing something. It's writing the offset of the consumers to itself upon a read. Yeah. So the reads also have to go through the leader. Yeah. So really all these other what are called the followers are doing, they're silently copying everything the leader does, waiting for the leader to fail so it can take over. It doesn't actually do any real work. It's really just maintaining copies of what the leader is doing. Yeah. So it's a sort of a passive follower. We can't even really use it for anything useful. We're just keeping copies of everything. We can't use it for reads. We can't use it for writes. We can only use the leader. Of course, if the leader fails, then one of these followers will step in and take over that job. Any questions or doubts? Okay, if not, we're going to move on to consumer groups. So the idea of consumer groups is that we can also distribute in some sense. I mean, there's different applications, but it can allow us to distribute the consumption of messages from a topic. So the idea is that maybe we have different, okay, I'm not sure if this is suitable for the example, but different fire departments. Maybe we have different stations, fire stations, for example, different police stations. Or in a more general setting, maybe we have multiple consumers and different machines that processor have a very similar function. Yeah, they can consume messages in a similar way. So we can put those consumers into groups. Yeah. So essentially, it allows us to divide a consumer into multiple consumers that may be distributed, maybe even decentralized in different physical locations that can consume from a topic. And we assume that if one consumer in the group reads a message and processes a message, it's sufficient. Yeah. So it's essentially saying that we're going to update the offsets for consumers at the group level. Yeah. So it's sufficient for one of the fire stations to process an emergency call, or for one of the police departments to process a certain call, for example. So the reads then for consumers that are subscribed to a topic, they're done by consumer group. So we keep offsets at the level of consumer groups. So we don't need to somehow have every consumer in a group read a message. So what this means is we're going to, write to one consumer. I think it would be better to say that a consumer can pull from the topic, and the offset will be updated at the level of the groups. This allows for partitioning consumers, and we can apply some load balancing within each group as well. So that's the concept of consumer groups. So there are different APIs in Kafka. So we've seen consumers and producers and what their roles are and how they read and write to different topics on Kafka. We have some more advanced APIs as well, two of which are the streams and the connectors API. So what are the connectors? The connectors are basically ways that you can interact with existing systems. Typically, for example, be a relational database, a NoSQL system, something where you want to use the information of that external system. You want to be able to reference it as part of the overall Kafka mediator. Another thing is that you may have consumers that are producers and producers that are consumers. So you may have, for example, a fire department or a police station that, yes, it's consuming lots of the messages, but it can also produce messages. Yeah, so it can also somehow push back to Kafka some messages to a certain topic or whatever it might be. Yeah, so this gives rise to the notion of the stream API, where we have, like in the sort of peer-to-peer system, where something is a client and a server at the same time. In this case, we have something that's a consumer and a producer at the same time. So we have producers here. We have consumers here who are just reading. So producers are just writing to Kafka. Consumers are just reading from Kafka, pulling from Kafka. We have connectors here, which is this idea of connecting Kafka with some external applications, database system, whatever it might be. It could also be an external, a different streaming application or something like Spark or whatever it might be. And then we have our stream API for these things that are consumers and producers. So the producer API allows us to append records to topics via push. Consumer API read records from topics via pull. Connector API allows us to read write to external components, for example, relational database, NoSQL database, other streaming platforms, whatever it might be. And then we call the streaming API the combination of the producer and consumer APIs. So we can both read and write effectively with respect to Kafka. Any questions or doubts? Okay, well, we're nearly done. So in terms of optimizations, we have a bunch of optimizations that I'm not going to get into in too much detail. So Kafka implements some optimizations such as log compaction, where it allows for compressing repeated sequential values. Why is this interesting? Why, I mean, we can think of lots of different methods, but why is compaction of repeated sequential values suppressed? Well, we have to think that Kafka, we're using it for streams, for sensors, right? So let's say we had maybe a temperature reading, and maybe the temperature reading was every second. It's quite likely we're going to get sequential values that are the same. Yeah. Maybe there's some other type of sensor where we're getting some readings that are quite likely to be frequently. There's going to be sequences or runs of the same value. So Kafka allows you to compact and compress these sorts of values. There is a couple of more low-level optimizations, such as direct disk to network. Actually, there's quite a few distributed frameworks that allow this. So if you have data on a disk, the typical way would be you read the data, whatever you've stored. Kafka, it's implemented in Java Scala. It has this Java Scala code that will read the data from the disk. It will parse it into its objects, and then it will send that over the network, some serialization of that, which will be deserialized again. So the idea of direct disk to network is to avoid the JVM. So to just move the data at the bytes directly and have the consumer read that data directly without having to deserialize and serialize the data standard. So also consumer and producer quota. So what happens if we have a producer that's just sending too many messages, or a consumer that's trying to somehow pull a massive amount of messages, or if we have, let's say, lots of consumers. So we can have set limits to avoid saturating the system for some very bursty producer, or maybe some greedy consumer who's trying to read too much or send too many read requests. So these are some optimizations just to give a flavor of some other stuff that goes on under the hood. There are some additional features that the Stream API allows to support. So we can have, for example, some sort of aggregation functions that allow us to count messages. We have joins to unify two streams. If we have two different streams of information and we want to do to unify them, maybe based on place, or based on a person, or based on whatever it might be. And we also have windowing, so we can define some windows, which are periods or intervals in a topic that we can define, read, and then process. So something as well that's kind of there's quite a lot of research going into this, but there's this notion of continuous querying, which I didn't mention. So continuous querying is like you register your SQL query, but you're not expecting an immediate answer. What you want is that the query will be processed over the stream of data, and when you get new answers, those answers are streamed to you. Yeah. So over, let's say we had something like Kafka, and it was taking in data from the stock market. It was taking in the prices of different stocks from different places that were being updated in real time. We also had some maybe producer from Bloomberg or some sort of business news outlet sending us information, and maybe some other producers along those lines. Then we can write more complex queries. And so we could use continuous querying to continuously monitor for stocks that are in the area of technology that whose prices increased by more than 5% in one day. And that has also been reported on Bloomberg, for example. So there are different languages for this. So Kafka has this Kafka SQL type feature. So typically these queries are defined on Windows, for example, one day would be a 24-hour window, and then we can answer some queries over that. So again, Kafka is one of the available frameworks. There are many available frameworks, but they all somehow cover a similar kind of use case or a similar kind of scenario. Yeah, Kafka is becoming one of the more popular ones, I would say. Yeah, so that's it. Any questions? Yeah, so just to briefly mention then, in astronomy, they're using Kafka. What are they using Kafka for? They have this Alerce project. They're going to be taking video of the night sky, and they're going to be trying to detect changes. So the idea is to look for transient objects like supernovae. So essentially, they have Kafka that's streaming in some raw data. It generates alerts, which are these interesting messages, and they're shared in Kafka. And then you have all of these different astronomy departments in different places that act as consumers, yeah, that can take data and they can also enrich data. So one consumer, which would actually be a stream, can take the raw alerts, try to classify what type of object it is, see if it exists in an existing catalog, enrich the data, send that to another stream that's consumed by some other department, and then they look at that and they might apply machine learning methods to try to improve the classification, and then it's passed along this way. And basically, in terms of real-time events, if there's some supernova happening, they can take real-time action to move a telescope to focus in on that particular object, a deeper telescope to focus on that particular object, for example. To give an example of where Kafka is being used in the, let's say, in the faculty. Questions? So there is one other thing to briefly mention. Sorry, you're probably thinking, oh, I'm going to go now, but 5 more minutes. We'll talk a little bit about the projects. So yeah, you're currently in the, you have until today to define your project group. Yeah, so you can define the people who are in your group. Please remember to do that. If you have some colleagues in mind, the deadline is today. Tomorrow, hopefully, we'll do the assignment. So you'll know, we'll fill in all the groups that only have 2 people, or maybe where there's no groups, and we'll do an assignment of the rest. If somebody doesn't want to do the project, it would be great to let me know, so that I don't assign you to a group. You can just write me a message in the forum. So we will have 20% for the project overall. Yeah, so it's quite a chunk of the grade. So class project, yeah, done in groups of 3. Goal is to use something you've learned in this course to do something to apply to a data set or a problem of your own choosing. Yeah, so there's going to be less guidance, and the idea is you get a bit more confidence and experience applying what you've learned here to a different scenario where there isn't a detailed enunciado. Yeah, so you get some confidence. You can see that you can apply these things to different types of scenarios. So I will assign the groups tomorrow, I hope. So the deadline is today for proposing your groups. So it's a good time to start thinking of topics or find interesting data sets. So there is a bit of a problem with all of the projects that we have, except for maybe databases, which is that we need to start the projects more or less around this time, but you've not seen all the topics yet. So we've not seen NoSQL, we've not seen Elasticsearch. There's a bunch of stuff yet to see. However, a typical kind of project would be to take some data set, some large data set, apply something like Spark, Pig, Hadoop on that in order to analyze the data set and come to some conclusions or find some interesting statistics related to that data set. So start thinking of topics, find interesting data sets. You can also work with Kafka. You can also work with the things we'll see in future classes, but you'll have to, unfortunately, define the topic more or less soon. So you'll have to register your topic, which will include the data set and your idea for what you want to achieve with that data set. And the work will be kind of parallel with the classes and the labs, so it's something to work on during the semester. And we should have a week or 2 towards, I think maybe a week now, because we already lost a week. We'll have a week as well towards the end that will be just for projects, dedicated to working on projects. Deliverables will be a 4-minute presentation, which will be a video, and a code repository. So it can be in GitHub or whatever with a documentation, a brief documentation in a README. So things we'll look out for when we're marking would be the difficulty, how ambitious was the project, appropriateness in terms of did you use something from the course, scale, as this is, procesamiento máximo de datos, big data, we expect you to work with a fairly large data set, not something you can easily load in Excel, for example. Good use of techniques, so did you choose the right things, the right tools for the job? Presentation itself, coolness. So how interesting were the data? Where was the data set? How interesting were the conclusions? Creativity. So we appreciate kind of creative ideas. Many will just be take a data set and analyze it, but we definitely appreciate a lot more creative ideas that are a bit different from others. And value. I don't know what value means. What does value mean? Value. Okay. So I guess it means, yeah. Did we learn something useful for society from this data set? Many people have analyzed, for example, crime data sets or certain geopolitical or social data sets that are quite interesting. So ambition is appreciated even if you don't succeed. So when you're choosing your project, it's quite good to be ambitious, even if it doesn't work out. So rather than play it safe, if you want to try something you think is a bit more ambitious, that's also appreciated for the market. Yeah, even if you don't succeed. So a very ambitious project that does a lot of work and gets most of the way there, but it kind of doesn't work out maybe in the end, that's more appreciated than a very safe, simple project that is 100% successful. Yeah. So yeah, ambition is appreciated. With respect to this as well, one major tip is that the cluster is usually a disaster the days before the project deadline. So it is in its worst state, and we're trying to put out fires and delete folders from HDFS and all sorts of stuff. The cluster will be a disaster coming up to the project deadline. So do try to get things done before that. And there's not much we can do. We try our best to maintain it and keep things clean coming up to the project deadline. But it's important. The only way to solve it is if you don't all try to use it all at once a few hours before the deadline. So do try to avoid that last minute rush. So as a final criteria for the course, must focus around some technique from the course. Yeah. So some people have maybe, before done projects where they use Spark to like take a data set and process it down, and then they use the cool tools to visualize and do all these cool things. It's okay to use other tools, but the focus, the core of the project where the bulk of the work must be related to the course. Yeah, it has to be the focus. Yeah, it's cool if you want to do graphics and you want to do visualization or whatever using some other tools, but the core of the work has to be relevant to this course. Expected difficulty, like how big or how small does this have to be? So I would say that the expected kind of scope of this is to do something similar to a lab. So the kinds of things you saw in a lab. Yeah. However, we're not going to give you any instructions or detailed guide, nothing like that. Yeah. So let's say the analysis from Spark from the previous lab of finding the actors, the best and worst actors. This is a sort of level that we're looking for in the project, but this has to be a completely original idea and a completely original data set. Yeah. We're not looking for something super massive. Yeah. But something similar to one of the labs that you would have seen. Data should not be too small. So you should have at least 1 million tuples, 1 million rows in your data. There might be some exceptions. You can ask us if you're wondering. Maybe sometimes there are data sets that have 10,000 columns. And in that case, you could say, well, okay, yeah, 100,000 tuples but 10,000 columns sounds pretty good, right? But in general, should have about 1 million tuples. However, on the other side, the data should not be too large. So I would say if your data set is going upward of towards 1 billion tuples, even if it's above, let's say here 250 million tuples, it's something we'd have to look at. It depends on what you want to do with it. So in theory, there's no problem with working at this scale with these tools, but it's just a question of using too much of the cluster. It's kind of, we have the shared cluster and it might take a lot of time, it might take a lot of space. There will be a lot of projects going on at the same time. So we're probably going to have in the order of 30 projects. So it's just a kind of a practical issue. And also it can be frustrating a little bit for you if you're processing a very large data set and it takes 20 hours to process it and it fails and so forth. It's sort of maybe too large. So maybe you could take in that case a sample of the data. Where to find explore data sets you could use, for example, Kaggle. You could try Google Dataset search. There are some open data related to Chile on different platforms that could be of interest. You can use whatever way you want to search, find data sets. Yeah? So you don't have to use these. some suggestions of where to get started. Go. So with respect to the projects, start thinking of some interesting data set. I would start with the data set, what kind of data you want to work with, then decide kind of what do you want to do with it. And then maybe think up some questions that you can answer from that data set. Yeah. And then we're going to ask you to propose that, which would probably be after the holidays. The week after the holidays, maybe around Wednesday or something like that, we'll be asking you to propose your data set and your topics by then. So the topic doesn't have to be super fixed, but it's just an example of some questions that you'd like to explore with the data set. Yeah. What technologies you'd like to use maybe as well. You can also say, well, we don't know yet, but we're thinking Pig or Spark, or we're thinking Hadoop or Pig, whatever you have some idea. Yeah. So we just want to have an idea that you've already selected your data set and you have some things in mind to work on for 2 weeks after the holidays. Yep. Okay. Any questions? Doubts? Nope. Okay. So on Wednesday we're going to have our lab with Kafka, and we're going to look at Twitter data. We're going to process streams of Twitter data. So see you on Wednesday.